All right. So this is a continuation from last semester's class. So this is 300. We're continuing on where we left off from 250, which is we left off at the right place. So 300 is supposed to be basically a data structures course, and we'll start talking about what that means today. I referenced linked lists and stuff like that a little bit last semester, but we didn't really talk about implementing linked lists, and we didn't do that, right? We didn't actually implement any linked list stuff. See, we have one new student, right? So tell me a little bit about your programming background.
So I have basically my associates in web and software development from WCTC,
Okay.
and I've been working as a software developer intern for the last year and a half.
Okay. So you feel like you know loops and objects and that kind of stuff. Fine.
Yeah.
Okay. So you basically had 250. Good. Have you done anything with linked lists or stacks or queues? So you're actually ahead of the game.
Right. I don't always know all the theory behind them, but I've used them.
I got you. All right. Perfect. Okay. Well, so I'm Mike, by the way. What's your name?
Emma.
Emma? Emma. Okay. Gotcha. Well, officially I'm Dr. Lippman, but I'm very informal, so I don't care what you call me. So Mike is fine, or most of call me Lippman, right? Yeah. The other professors are significantly more formal, so just be prepared. Okay, so this is the normal jazz for the class. Book we're going to use is another Xi book. It is different than the one from last semester. This one's specific for data structures. So if you go to xibooks.com, you enter in this code CUWCS300 Lippman Spring 2017, click subscribe. It's $40 for the book, a little bit less than I think the one was last year. So it'll, I think the book you get it till like the middle of June or something like that. But in any case, this is the book. We're going to start off by talking about some searching, sorting stuff, which we did actually talk a little bit about last semester, but specifically we're going to be looking at, did we do merge sort last semester? Yeah. Okay. So we'll kind of breeze through this first section pretty quickly. But really what we're looking at is this big O notation from here. As you look through this, you can see this book is designed for C, C++, as well as Java. So any section that says Java next to it, that's the one we're interested in. Have you done any Android programming stuff? Okay, because we actually use the Android environment in here.
Yeah, I have a whole course on that.
Okay, cool. All right, so anyways, that's the book, and we will look at the quick sort thing here, though, since you haven't actually had a quick sort. It's very related to merge sort. It's a recursion-based thing. So we might even get to looking at that a little bit today, as well as the difference between selection sort and insertion sort. So we'll kind of go through that. Then we get into lists and stacks and queues. Then hash tables. I actually might flip-flop and do trees before hash tables, but we'll see. And then we kind of finish off with graphs. Traveling salesman problem is usually what we're looking at in graphs. So let's see, do they deal with that? Yeah, Dijkstra's algorithm, shortest path for traveling salesman. So this is going to cover all the stuff we would normally cover in here. And just like last semester, if you look at searching algorithms, the book is less reading and has a lot of interactive things in it and stuff like that for you to kind of, it'll ask you for, how many search elements does it take to find a certain number using a linear search versus a binary search, that kind of crap. So after we read about them, you'll be able to go through this. And what's nice for me using XiBooks, the reason why I've kind of adopted these, is I'm able to see that you guys are going through the book and making progress, so that when you suck on an assignment or you suck on an exam, I can go back and say, well, was this student putting in the effort and trying to keep up with class? If yes, then okay, let's try to evaluate why they're struggling. If no, well, then we know why you're struggling. So it's that kind of dealio. Just like last semester, I'll put all of my lectures online on YouTube. So, you're all adults. I'm supposed to take attendance every class, but I don't because I'm a rebel. But we do have pop quizzes. So you will have attendance taken when I have a pop quiz. If we go back to the syllabus here and we scroll down here, you'll see that the breakdown's the same as last semester. So 40% of your grade is homework assignments, which will be, almost all programming, maybe the occasional paper, but a lot of programming. And then 20% will be quizzes, and quizzes are always going to be that beginning of the class 5-minute quiz. Sometimes I'll announce it before class, but I almost always will give you that threat of a quiz. Here's some reading, there might be a quiz, and usually I mean that there will be a quiz, but sometimes I forget to give the quiz. So, whatever, but that's your risk. So you're all adults. If you have something better to do than come to class, it's fine, but you're risking missing a quiz. And remember, those are 20% of your grade. And typically, throughout the semester, there's usually an opportunity for 1 or 2 free quizzes that come up. So, I wouldn't necessarily 100% bank on that, but that has been my experience. So, but if you do have to miss a class for an emergency, something legitimate, email me or text me or connect with me on Slack and let me know. And, as long as it's a reasonable excuse, I'll just excuse you from the quiz. So, I don't want you running to a class instead of like visiting somebody in the hospital or something like that. So, in any case, but, hey, I got home from work late last night, so I had a little trouble getting up this morning. That's going to get a laugh from me, which I encourage you to entertain me, but that's not going to work. Normal grading scale, 90, 80, 70, 60, blah, blah, blah. Questions, comments, concerns, early bribes. Okay, where's Van?
I don't know. He wasn't in class yesterday either.
Well, I know why he wasn't in class yesterday.
He's at Starbucks probably.
Huh?
He is not in the campus. He will come next class.
Oh, he told you?
Yeah.
I texted him this morning, wanted to know where my coffee was. It's garbage. I have one student who delivers me Starbucks every class. And he just barely passed last semester, too. It was terrible. Oh, maybe he just responded to me. Let's see what he got.
You got your new MacBook.
Yep. I'm fixing my car at the moment. I don't know what happened. My cousin took the car and leave it home today, and the car won't start. I don't know. It's all broken English. All right, so syllabus makes some decent sense. Normal standard crap. Book makes some decent sense. A little bit cheaper than last time. I got some pretty decent feedback about the Zybook last time, so we'll stick with that. Let's go this direction then. Oh, you did mention the new MacBook. You want to know something interesting?
Yeah.
So this is the new MacBook Pro, the crazy expensive machine that's not worth it. I mean, it's nice, but it's not worth $4,800. But what's interesting, if you've had a Mac before, when it comes with the power cable, right? And with the Macs, it's got the white little box thing, power cable, and then it has an attachment on it where you can either plug the box directly into the wall, or you can pull that off and it comes with like an extension cable where you can have a wire coming off it to plug into the wall. Kind of handy, right? Okay. But this one also then has a USB-C port on the side of it instead of having the built-in thing that leads to the computer. So, it's a removable cable. So if that frays, you don't have to replace the whole box. You can just replace that cable. So that's nice, that part of it. But the power cable itself does not come with that adapter to go to a cable. What comes with the $4,800 computer is the thing that just plugs directly into the wall, blocking all your other outlets, right? That's what comes with it. If you want the extension, it's $20 to Apple. Good news is that they didn't change the design, so I was able to use extensions from previous power chargers that I had. So that's all kind of bad. Here's the worst part. So let's say you want to get a second power adapter. Because I want to charge it at home, I want to charge it in my office, I want to always have to drag the adapter with me. So you can go to Apple and give them $80. for a power adapter. Same price as the old power adapter was, but you don't quite get as much stuff. First of all, they're not giving you a little extension cable. Well, they weren't going to give it with the $5,000 machine. Why should they give it you with the $80 charger, right? So, but you also, for $80, can't actually charge your laptop. Apple's taken advantage of the fact that that USB-C cable is removable and said, oh, you don't need that with your replaceable one. They don't give you the USB-C cable that goes from the power charger to the laptop. If you want that, that's another $20 to Apple. So it's really a $100 charger. And if you want the extension thing, it's a $120 charger. How much does that USB-C cable cost Apple? $1? Max? I mean, we already knew they were borderline unethical, but now they're just like rubbing it in your face. It's like, yeah, you want to actually charge your laptop? Yeah, $80 isn't going to quite do it, pal. Just stupid. But I guess the good news is, since USB-C is going to be a standard, before you had the MagSafe adapters, which were kind of neat because you could just kind of get it near it and it plugged right in. And plus you got a little light letting you know that your laptop was actually charging. No light with this one. Yes, well, it looks just like this. There's no light, no indicator that it's charging or done charging, nothing. You got nothing. But what's nice about it is, since it's not a proprietary technology, you're going to have, I assume, a lot of third-party chargers out there. So I just have to hold out until USB-C gets kind of adopted by everybody, and then yeah, I can't plug in a normal USB device in here. I have to have a dongle that's USB to, or USB-C to, like a 4-port USB hub.
Does that come with it?
Oh, no. Apple does not sell one, actually. Yeah, so as far as Apple's concerned, if you want to work strictly through the Apple Store, you can't plug USB devices into your new $5,000 laptop. Oh, but I tell you. I mean, I'm all about innovation, so I actually don't have a major issue with them getting rid of the normal USB ports and going with USB-C to kind of push that transition. I'm relatively okay with that. But come on, don't give us the extra length cable for the power cable. Include the USB-C cable when you buy a new charger for $80. It's just ridiculous. So, and this little magic bar thing is the only thing I found useful, is that instead of typing in a password, I can do the little fingerprint scanner, and that's worked well. It's instantaneous. The escape button I use very often, and that's on the magic bar thing, so you're never actually sure whether you hit it. So I can't decide if I love the new keyboard or completely hate it. It's somewhere. It's not in the middle. I either really, really like it because it's pretty, gives you a lot of feedback. Makes a lot of clicky noises you'll hear in a few minutes, but the magic bar itself appears to be fairly gimmicky. Although we had an interesting thing happen in class last night. I will reproduce it for you. In the research class last night, let's just start a new slide set since we hadn't started. Okay, here, I'll show you. So we were typing the word tennis in there because we were talking about automation and automating line calling in tennis. So I type in tennis, and on the magic bar, I get the little tennis emoji. $5,000. What can I say? Can you do auto tennis emoji on yours? See? Plus, another feature is you accidentally hit the Siri button pretty often. So Siri gets a little chatty. So there it is. That's your intro. The screen is really nice on it. It's my previous one was the still a Retina screen, and it was nowhere near as clear as this one. So they did a nice job with the screen. Not $5,000 nice, but whatever. So let's go here. All right. Let me check real quick to see if some of the stuff that I had cooking is done cooking. Okay, well, I guess we'll let that guy keep cooking. I didn't have eclipse on this guy, so I came completely unprepared, but that's okay. We got to talk about some theory stuff first anyways. Okay, so if we kind of follow where the book is going with this, when we start off with searching and sorting algorithms. Now, remind me, what searching and sorting did we cover? It would have been relatively early last semester. Did we cover anything specifically? I seem to remember we maybe did an insertion sort.
We've done a bubble sort, either this or 200.
Okay, but that's a while ago?
Yeah.
Okay, so we could probably review some searching sorting stuff? All right. Well, let's talk about searching and sorting at the high level anyways, at least to start off with. Let's just do searching for a starting point. All right, so you got a collection of data, whether it's just strings or numbers or objects. And just since we've already covered objects, that's going to be kind of where we're going with this. In our assignment, we'll be looking at searching and sorting objects of things. Last semester, we were working with like a player object near the end, right? And so a player object had like a first name, and I don't remember if it had a first name, last name, jersey number, and like a skill rating or something like that. I think 4 attributes to it. So what if I wanted you to sort a roster of players based on their skill rating? So now you're going to have to dive into each individual object and compare their skill rating to actually perform the search. So the nature of the data that we are searching, or the nature of the data that we're sorting can change depending on whether we're sorting something that's a primitive type. What are our primitive types again? Int, long, double, float. I think we're missing 2. Byte. Now we're missing 1. The least used of all of them. Remember, these guys came from the original language. Remember our old slide? Let me pop that open real quick. We talked about the history of these languages, and we already had double. So all of these languages came from C. We have Boolean. So C was our core language. So all these primitive types came from the time of C. So 1968-ish. Now remind me for a second, why do we have, so far what we've mentioned is we've mentioned byte, we've mentioned int, and we've mentioned long. Short, okay, so short's the other one. All right, why do we need so many different ways of holding whole signed numbers? What do I mean by a signed number? We can hold positive and negative numbers. So that reduces we use one of those bits for the value. So, if we reproduce our chart over here, I might want to refer back to that here in a few seconds. Okay, so we have byte, short, int, long. I told you I sort of hate this keyboard, but see, I just pressed the escape button. I wasn't even positive I did. Char, float, double, Boolean. All right, so byte, short, int, long, all of those guys are signed integers, signed whole numbers, right? They can hold positive and negative numbers. A byte, this guy is 8 bits. A short is 16 bits. An int is 32 bits. A long is 64 bits. What kind of values do chars hold? Unsigned values, okay, so far so good. Specifically, unsigned integers, right? Even though chars ultimately represent characters, A's and B's and question marks and commas, those things, at the end of the day, chars are 16-bit unsigned ints. All right, and why do we store them as ints?
Integers mapped to characters in ASCII or
In Java Unicode, right? Yeah. So we have character sets. We have the old school C-based character set, which was ASCII, which had 256 unique characters, and that was an 8-bit value. And more recently, we have decided that characters beyond the English language actually exist. So we use the Unicode character set, which is a 16-bit value. So how many total characters are in the Unicode character set? 65,536. So their index 0 to 65,535, which you'll find is 2 to the 16th power minus 1, because we use the 0 to that. All right. So our 8-bit values here, bytes can hold negative 128 to positive 127. Shorts can hold negative 32,768 to positive 32,767. And if you take the absolute value of those and add them together, you'll get 65,535. Ints can hold negative 2 billion. I think it's like 2.1 billion. So here, I'll add to my accuracy. 2.1 billion to positive 2.1 billion. And then longs are negative huge number, or I guess negative tiny number, I guess. I think it's something like 4 quintillion. 2 to the 63rd. It's 9. 9.2. Is that quintillion or quadrillion? Big number. Big number is what they are. So negative huge number to positive huge number. Okay, and these are all of our primitive types. So if we can't store our value in that, then we can move to object types that allow us to hold arbitrary size values. Did we look at big integer at some point? Ever looked at big integer? So big integer would be a Java object type that allows us to hold arbitrary size numbers we can have a 4,000-bit value. It's going to get slow. Okay, we're about to talk about complexity and time complexity and space complexity. And so in that particular case, it's a time complexity issue. You want to hold a number with a zillion digits. That's cool. As long as you have the memory to store it, we'll do it. But to actually do computations with that is going to be a time complexity issue because you're dealing with lots and lots and lots of buckets. Okay? So when you start dealing with arbitrary size values, you're dealing with a definite slowdown. So let's ask more of a theoretical question. And a couple of you in here who had 325 should definitely be able to get the answer to this. Which would be faster? A long doing doing addition with a long, or doing addition with a big integer with 64-bit values? Okay, you think the long would be faster? Why?
There's less buckets to go through.
But I've said they're both 64 bits.
Okay.
We're representing a 64-bit number in both of them.
I thought that the big number would you still have to go through those buckets even though.
You still do, but ultimately what it's going to come down to is whether it's being done in software or at the hardware level. So because these primitive types are known quantities, right? We know we have something that's capable of doing 8-bit values. So for those of you who had the architecture class, I think was just a couple of you in here, right? But the rest of you will have 325 probably in the fall, I think. You'll have the architecture class with me. One thing we learned about in there is we have these hardware registers, basically, buckets of memory that live right next to the CPU. Fast, really, really, really fast. And we had 8-bit registers, and we had 16-bit registers, and 32-bit registers, and we knew with some of the newer architectures we had 64-bit registers. So if we have a modern processor that has up to, actually some of our modern processors have 128-bit registers as well, but if we have a modern processor that has 64-bit arithmetic registers in it, we can fit along in its entirety in a memory register that sits right next to the CPU. It's going to be as fast as it's going to get, right? Now, if you go over to a big integer, so an object type for holding that same 64-bit value, you got to keep in mind that that big integer was built to hold arbitrary size values. So even though you purposely only put a 64-bit value in there, it was implemented to hold arbitrary size values. So it couldn't just assume that we can use a 64-bit register to do this math. So it's handling all that arithmetic at the software level. So it's almost like a virtual machine doing your math, if we're kind of following that whole Java as a virtual machine. So we have a middleman. So we're doing almost bit-based math with carries and stuff, using even more memory potentially, because we're going to have a couple of extra variables for those, for the carry bits and stuff like that. But it's also going to be slower because all of those arithmetic operations are going to turn into instructions for the CPU, magic tricks on the CPU. That makes some sense? Okay, so when you can use primitive types, you should use primitive types, especially if you care about speed. Okay, I'm going to come back to that idea of, do we care about speed here in a minute. Let me actually create a slide. Do we care about speed? And then I'm going to have another slide. Do we care about memory footprint? All right, so just to kind of complete this guy here, floats are, what is it, 32 bit by 16-bit after the decimal point, signed. Doubles are 64-bit by 32-bit after the decimal point, signed, and these are decimal numbers. Okay, and then Booleans under the hood, these guys can be represented as just a bit, a 0 or a 1, but they're actually implemented in terms of bytes. So, if we want to talk about these from a theory perspective, this is a 0 or a 1. So these are 1-bit values, but we're going to be stuck with the implementation for the language we're working with, which our smallest implementation is a byte. Okay, so we're going to store a 0 and 1 in a space capable of holding plus or minus, or negative 128 to positive 127. So plus or minus 2 to the 8th power, 2 to the 7th power. All right, so that makes sense for our primitive types. Kind of remember those guys now? All right, so let's go to this dude here. So this kind of starts us thinking down the lines of what we talk about in 300. And so do we actually care about the speed of our applications? Or maybe I said should. Do you believe that eventually you'll care? Right now, maybe most of you care about whether or not your stuff actually ends up working. Right? I don't care if it's slow. I just want it to work. Okay? But if you kind of imagine yourself in a couple of years, you're out in industry, you're writing software for some company, they're paying you, they're paying you decent money to do it. Do you care about speed? Do you care how fast your software is? Okay, you say yes. Tell me why.
Because as it gets more complex, if it's slow, then it can get really slow for the user, and that makes the user not want to use it. If they don't want to use it, then
okay. So really your answer is maybe. Depends how complex the problem is,
true, yes.
right? Yeah. So as problems become more complex, and sometimes the type of complexity makes a difference, all right? But as problems become more complex, the speed of it might become noticeable to the end user, okay? Now, you've been doing a lot of web programming stuff, right? Okay, so in her world, things actually are even, speed might be even a bigger issue, and sometimes it's out of her control. Because now she's got other things in the middle, almost like our virtual machine argument. You got internet connections, you got the speed of various web browsers. Some web browsers handle JavaScript faster than other ones. Every single time a new browser comes out, whether it's Chrome or Safari or whatever, one of the things they brag about it's 13 times faster at handling JavaScript than the previous guy. Like, okay, whatever that means, right? And most of the time, when we think about simple JavaScript, that's meaningless. If we go back to some of the early uses of JavaScript for like validating web forms and stuff, we're not going to send your username and password to the server unless you actually typed in a username and password. Let's handle that on the web browser, on the client side. Remember, we talked about client side versus server side earlier last semester, I think, when we were talking about the difference between our web languages and our native languages, I guess what I refer to them as. But there's a lot of moving parts when it comes to web programming, and some things are beyond the programmer's control. But you have to deal with different browsers and how browsers handle different things. So sometimes you have interface problems where you have to write the interface 3 different times depending on which browsers you're using. So speed might be significantly more of interest to you as a web programmer because most of the time you're looking at it through the eyes of the end user's experience. And that's okay because that's equivalent to what we're dealing with here. But if we're talking about native languages, if let's say just a common problem, not an overly complex problem. If you write it in the worst possible accurate way versus the best, most efficient possible accurate way, do you think a user is going to be able to discern the difference in runtime for a program that's running natively on a computer, not reliant on an internet connection, not reliant on how fast a browser renders it, that kind of stuff? For I say most. For a human being, can we tell the difference between 2 microseconds and 9 microseconds? We don't feel that. That's not human level. Now, if you have something that it starts compounding, so fine. Well, 2 to 9 microseconds, that's not that big a deal. Well, if you're going to do that operation, 4 billion times, now that's time. Okay, that starts turning into actual measurable human time, seconds and minutes and hours and days. We notice days, okay, depending on the kind of level of alcohol and stuff like that, but it's dry campus. Yeah, I forgot that you're all upstanding. That's right. All right. So, real answer here is, do we care about speed? Sometimes. Why does it want to capitalize it? What happens if I hit body? I didn't do anything. Oh, it did. It changed my options up there. I don't like that. Nailed it. All right. So, the answer is sometimes. So we might say when the user might notice. Okay. And even then we might not care about speed. Just because the user notices the difference, maybe they barely notice the difference. Maybe something is, it takes a second instead of a half a second, let's say. Now, if it's something a user is doing very, very, very often, that adds up. That's going to be something that starts becoming noticeable. You might want to spend time. But if the difference is that I can write that 1 second solution in 10 minutes versus I can write that half a second solution in 2 days using some sort of, crazy mathy algorithm or something like that, something significantly more complex to implement. And, your employer is paying the bill. And it's something that a user is going to use one time when they're installing the application, let's say, when they first double click it to install it, and it takes, look at this. This has got to be internet connection related for my Eclipse install. It's just been sitting here. Very interesting. Should we cancel and start again? See what happens. Maybe it's because I went between Wi-Fi hotspots when I was installing it. Who knows? But clearly they didn't pay a whole lot of attention to speed on this. They would have probably just packaged more of it with the download, but whatever. The point is I only have to do that one time, right? So if it takes a little bit longer to install, not the end of the world, because it happens one time. It's something that's happening constantly. We then actually care about it. Okay, so when the user might notice, we care about speed. What about memory footprint? The answer probably sometimes on this one as well. Okay, so when is the sometimes? When do we care about memory footprint? And keep in mind, our answer here is going to be very different than our answer might have been in the 1970s or the 1980s. That's kind of gets back to what we just talked about with our primitive types. You go back to the late 60s, the 70s, the 80s, the 90s. Memory was expensive. I used the example last semester where in I think it was 1996 or 1997, something in that ballpark. The computer I had came with 8 megabytes of memory, and I added another 8 megabyte chip to it. Now today you go to Best Buy and you pay retail for a 4 gigabyte chip, and it's like $40, right? Not very expensive, relatively speaking, for a 4 gigabyte chip. How much bigger is 4 gigabytes than 8 megabytes? So 4 gigabytes is 4,096 megabytes divided by 8. 4,096 divided by 8, so it's 512 times the size. So today I can get 512 times the size of 8 megabytes for $40. Okay, so if we divide $40 by 512, 8 megabytes should cost, if we round up, about 8 cents in today's dollars, right? Now you deal with inflation and stuff like that. Maybe we're dealing with a quarter, something like that. Okay, in 1997, did that 8 megabyte chip cost me a quarter? Anybody remember how much it cost? $1,000. $1,000 for 8 megabytes of memory. Okay, and that was after the price of memory had already significantly come down. That was after it got cheaper. All right, so you roll back and you start thinking, okay, early 90s, 80s, 70s, when back in the 80s when Bill Gates had the famous comment that you'll never need more than 32K of memory. Right now, getting back to the bashing on Apple thing with the new MacBooks, this is a completely decked out new MacBook Pro, and the maximum amount of RAM I can put in is 16 gigabytes, which is the same amount of RAM as I had in my 2012 MacBook Pro. Why can't I put more RAM in it? This is dumb. It's just dumb, is what it is. All right, so, in any case, memory used to be very, very, very expensive. So our answer to this question of do we care about memory footprint is very, very different today than it would have been in the 80s or 90s and stuff like that. But we are programmers today. We want to appreciate maybe what the world looked like in the 80s or 90s and kind of, the conveniences we have today. That's why I show you so many under the hood things. Okay? But the reality is that generally we don't care about memory footprint today unless we start running out of it. Right? Okay, so for me, I'm only going to care about memory footprint if my 16 gigabytes doesn't cover me. Okay, because at that point, I'm screwed. I can't add more memory to this. This whole thing is glued together and everything's soldered to the motherboard. So there's no adding more RAM. With your common laptop, that's a third the price, and it's not made of titanium or whatever this thing's made of. You have memory upgrade slots. A lot of times they might come with an inconvenient configuration. I've seen some machines come with like 6 gigs of RAM where it's like a 2 gigabyte chip and a 4 gigabyte chip. So what's the worst that happens? You throw the 2 gigabyte chip in the blender and just wave goodbye, and you spend your $40 and get the 4 gigabyte chip and move on with life. Right?
Dell finally started giving us 1.8 instead of 2 4s.
Oh, nice. Yeah. In laptops?
Yeah. They'll have 2 DIMM slots, and we'll get an 8 gig stick.
Okay, so actually that's something that's happened in the last year or so then, because it was pretty rare to find machines that would accept 8 gigabyte DIMMs in a laptop, and part of the problem was it was not cost effective to build 8 gigabyte chips, single chips. I think I read last year some point, and this is not in laptop memory, this is in desktop memory, but those things get blurred anymore, except for the fact that laptops just keep getting skinnier. So like now you got to make special stuff for them. But I think, was it Samsung that's making 64 gigabyte sticks? They at least have them. Yeah, I'm sure it's not cost effective, right?
I think they just like released that in their press conference thing.
Okay.
It's like brand new.
Yeah, I mean, I'm sure it's crazy expensive, and then you have to get some sort of Samsung,
Yes.
$2,000 motherboard that can accept the 64 gigabyte chip. So
The only one that can.
yeah, so now you have 256 gigs of RAM or something like that in your machine, and which sounds cool. I remember I was when I was a lot younger, probably before most of you were things. I worked at a computer place, and we thought it was this one guy, seemed to be made of money or something like that. Ordered a computer that had 128 megabytes of RAM in it. We thought the guy was insane. Who needs 128 megabytes of RAM? I mean, like he was the most expensive chips, and this, so, I think we could fit 4 chips in there. So those were, they were 32 megabyte sticks, and those were crazy expensive. I mean, a 32 megabyte stick back then must have been, $4,000 or something like that. He wanted 4 of them, and it's just ridiculous. Like, who needs 128 megabytes of RAM? We just laugh at that today, right? Like, well, everybody. I mean, my toaster has a gig, which used to be a funny joke, but now there are toasters that have like smart stuff in it that might have a gig of RAM in them. I haven't gotten the smart toaster yet. I actually don't understand the point of normal toasters anymore. I like toaster ovens, have the front panel thing you put stuff in. But the pop down, that seems to be an antiquated technology.
Kind of a pain.
Yeah, because then you get crumbs in there, and then my wife complains that she has to clean it.
And every once in a while, your bagel or something is like stuck.
Oh yeah, then you got to burn yourself. Yeah. Or Pop-Tarts fall apart. Pop-Tarts are not made as rigid as they used to be. These are...
It's structural issues.
Yeah, no, I mean, there are. I mean, they have lowered their standards. It's kind of I bet you it's similar to the whole thing how Twinkies taste different now, right? They sold the company, now they're using probably more cost-effective ways of making them. They're not making Pop-Tarts like they used to. I mean, Pop-Tarts, you used to have to stretch out your jaw to bite through them. Not anymore, they just fall apart in your hand. I mean, you can't hold a Pop-Tart on the end and bring it up there. I mean, it's going to... You all know this is true. This is fact stuff. All right, so memory footprint. Sometimes we care about it. When? Well, when we might run out of RAM. Okay, well, under what circumstances might that happen? So when our computing, we have to think about what other things are going to be running on this computer. If you're writing an application for a server, so let's say we're writing a web server. So out of curiosity, what's a web server? We talked about it last semester when we were talking about the client server side. What is a web server? It's a computer program, right? And what does it do? What problem does a web server solve? Okay. Let me back up one question. How many of you think that writing a web server is a pretty complex thing? Does it sound like it would be a hard project to write a web server? Sounds like that, and that seems to be that web servers, they sound intimidating to some level, right? Okay, and it's probably somewhat of a hard project to write, something like that. Okay, so now we think about the types of problems. So you said it transfers files. Okay, what else does a web server do?
Handle incoming connections.
Okay. Yeah, it accepts incoming connections and then the requests associated with those connections. So, if all of us go to Google right now and we type in we go to www.google.com, nobody does it anymore. We just put it in our search bar, right? But whatever you go to Google, you do your search. That's a request, opening a connection to Google's web server. It's sending them a request. Google's then doing some stuff behind the scenes, and that's Google's special sauce, right? Is their whole search engine stuff. Okay, so Google isn't a web server. Google is a application that lives on a web server. Okay, it's accepting requests and then doing some stuff behind the scenes. But the point is that Google's web server is accepting your search request and then passing it off to the Google application that goes and does its magic. Okay, and then ultimately, as you said, it's sending data back, transmitting stuff back. Okay, so it accepts connections, accepts requests, sends files back. Writing a web server is actually fairly simple. I mean, it's got some network programming in it, but even then, right when we hear network programming, we might say, well, that sounds kind of hard. Anymore, most of our languages have network crap built into them. So you include a couple of libraries. You say, okay, I'm going to create a socket, and I'm going to say, listen for incoming connections. Done. We might even do something like that this semester. We'll write a web server that has a socket and accepts a connection and then spins back up and waits for another connection. Spawns off a thread to go and deal with that guy. Like, oh, threads, they seem scary. 2 lines of code. Done. Move on.
Even with that many requests at one time?
Well, that's now you're talking about getting into more what's the difference between a web server and an enterprise level web server, and then you're starting to talk about some network equipment that does load balancing. So Google isn't just a single machine sitting there with a copy of Apache web server running on it. It's I'm sure they have a server farm of web servers that all hook into another server farm that are all running Google's the Google search application. So when an incoming connection comes in, it gets diverted to the line of web servers that's least long right then. So that it's fast. Because Google's always fast, right? And it's fast because they have a lot. It's like I think I usually use the example. I probably used it for something last semester too. But it's like when you walk into a McDonald's. Okay, if it's during the lunch rush and there's one register open, that would be your common plain Jane won't work for Google web server. Okay, because replace McDonald's with like Bob's Sandwich Shop, which probably isn't getting overly crowded at lunchtime, day one, until they get a name for themselves. They have a lot of Yelp reviews and all that crap, right? So, you got 2 or 3 people. Web servers are pretty fast. They can handle 2 or 3 simultaneous connections, no problem. But now you got lunch rush at McDonald's, downtown Chicago. Busy, okay? They're going to have a little bit more than 1 register open, right? Otherwise, the line's going to be out the door and around the corner. They're going to have 5 registers open. And you come in and you kind of filter to whatever register is currently open or whichever line is the shortest. Some places have 1 line that filters, and then you kind of just whoever can help you next helps you. Otherwise, you roll the dice, you pick the line, and hope for the best. So in any case, Google's web server would be more like that, but with more than 5 lines, right? Because Google gets crowded. Since we started this conversation, how many millions of requests has Google taken? Many, right? Many. All right. Now, as us pedestrian computer programmers, when we're writing our software that runs on our single machine sitting here, things that we have to worry about is, how is our software going to run in the wild? Is this something we're going to distribute to somebody? Is it going to be running on a single standalone machine? And is that machine purposed to only run my software? If it is, then I can stretch out a little bit, right? I can use all the RAM in that machine because I know I don't have to, minus what the operating system's going to use. But, I don't have to worry about competing for resources with other applications running on there. Now, if I'm one of 50 applications that are going to be running on that machine, take Concordia, for example. We have servers and things like that, but it's possible we might have 1 or 2 machines that are dedicated for a very specific task. But in general, we're going to double or triple or quadruple or 30 dip a machine to run many services on one machine, just because of the name. I mean, you got dollars involved, you got space involved, you got the we have a relatively smaller population of students involved compared to a very large state university or something like that. So those decisions get made based on the kind of the importance of what the purpose of the machine is. So depending on the nature of our software and what we're writing it for, we may care about memory more than other things. Now, outside of that, we also have to think about the complexity of the software that we're writing. If it's pretty simple software, we can pretty much just assume that, oh, this guy is not going to be a memory problem. I mean, it's going to has an array of 100 things versus an array of 1,000 things. Like, oh, it's not that much. Who cares, right? If you have 1,000 integers, that's 1,000 times 32 bits. So that's 32,000 bits. So we take 32,000 bits divided by 1,024. Now we're at kilobits. Then we divide that by 8. Now we're at kilobytes, right? So 3.9 kilobytes. You want to multiply that by 1,024. Now you're at, divide it. Divide that by 1,024. Now you're at megabytes. Divide that by 1,024. Now you're at gigabytes. Inconsequential when you deal with the amount of RAM that's in our machines today, right? We don't care. 1,000 elements in your array, even if it's our amazingly gigantic player objects that are holding on to 4 attributes. Take a 0 off there or something like that. Inconsequential. So most of the time we don't care. As a programmer, though, we need to be able to discern when we should care. When are we working with something that might affect the end user or might affect the environment in which our software is running? These are things that we need to be able to do, and that's kind of what this course is about. So outside of the searching stuff, let me kind of give you an introduction to this idea that we're going to spend most of the semester on, and this idea of something called data structures. All right, so we've already been introduced to one data structure. Actually, we've been introduced to 2 data structures in here. We've been introduced to arrays, right? And then whatever. Then at the top level, we don't necessarily know what's happening under the hood, but we've also used array lists from Java. That was something that the book last semester introduced, right? And we didn't necessarily know how they're built, but it was kind of like we went to Home Depot, we got the better drill or something, and like, oh, this is better. You have no idea what's in it, but it's better. All right, so array lists are kind of like that. So array lists are going to be closely related to what we're going to be dealing with early on in here, which is this data structure called a linked list. Okay, so we'll understand what those guys are and how they're built and why they are better in some ways and worse in other ways. Okay, so let me ask you this. So how many of you believe, or before I just made that last comment, believed that array lists were upgrades to arrays? Seemed like, oh, arrays are antiquated. We don't need arrays anymore. Array lists are improvements. They're better. That's fair enough to assume, right? How many of you now believe that's true after my last statement? Do you think there's probably some pros and cons to arrays lists and some pros and cons to arrays? Okay, so when we talk about arrays, what's a negative about arrays? Go ahead. It's build once, then you're stuck with it, right? So we are limited to original construction. So if we build an array capable of holding 10 things, we're stuck with an array capable of holding 10 things. Okay, remember we talked about arrays. Let me actually just bring that other slide up here. Talked about arrays last semester, and when we explain them here, is this an array? That's a scope thing. That's a scope thing. Is this an array thing? Yeah, it's an array thing. All right, so we talked about arrays. When we build an array, they get built inside of contiguous memory, right? So that's memory in a row. So that means that when we request an array, so we say something like an integer array AR is equal to a new integer array of size 3, what are we doing? We are saying I need three 32-bit buckets in a row. So I need 96 buckets of RAM, 96 bits of RAM next to each other somewhere in memory. And we're asking this new keyword, which is our real estate agent, to go out and find us that memory. All right, so it's going to run out. It's going to find us a place in memory that has that space, and it's going to say, okay, this is yours. Okay, so it's going to bring us back the base address of where that array lives. Okay, this is our house. Pretty similar to real life. Okay, when you get a mortgage and you buy a house and you have an address, you can't just decide you want your house to be 10 times bigger because you don't own that land. You know, that's now I'm building into my neighbor's land and his neighbor's land and so on and so forth. All right, so it doesn't work that way. Okay, so really arrays are much like our real estate in real life. You know, we get it once and we're kind of stuck with what we have, except it's even more restrictive. See, with my house, I have I plot of land and stuff like that, but I got a little wiggle room. You know, I could throw a sunroom on or something like that, and as long as I could just take it up to the border with my neighbor, I'm cool. Arrays don't give you that flexibility. It's the exact size for what you required. Any more stuff, you got to build it. You got to build a brand new house. All right, so arrays have that limitation. To their original construction. You're stuck with that size. Now, what's positive about arrays? That contiguous memory is a pretty important piece to it. Go ahead.
Because it's contiguous memory, we can calculate the address of any of the buckets based on the base address.
They're fast. Yeah. They're fast. We can get to bucket 3 of that array. Isn't a down swipe supposed to show me the screens of the current application? I mean, this shows me all my screens. Probably a configuration thing I got to go do.
Mission control.
So if I want to get to bucket 1 of this array, I go to the base address, I add to that 1 times the size of the value it was built to store, which is 4 bytes, 32 bits. So 100 plus 1 times 4 is 104. That's the memory address where that bucket lives. I can compute it mathematically. I can just go there. I can say I need the value at memory location 104 in memory. I don't have to traverse the array. I don't have to go in the front door and walk to the back of the room in the back of the house to find what I'm looking for. I can just go there. So arrays are fast. All right, so pros and cons of arrays. We're limited to how we originally construct them, but they're really fast. So if we know how much stuff we need to hold, arrays are the better choice because they're fast. Now, an array list under the hood is going to be built like we presume it's either going to be built like a destructive array, which means that what we don't know doesn't hurt us. It's like, oh, you want to add something to your array list? Yeah, no problem. Just append a new value on. You wanted 3 things originally, now you want 4? No problem. Under the hood, they're destroying houses, okay, building a brand new one that's a little bit bigger and saying, oh, he doesn't know any better. And it happened so fast, he didn't notice. Who cares? So that's one option, right? We don't know. We don't know what's inside of that more expensive screw gun that we got from Home Depot. It's just better, right? Okay, so that's one possibility. Another possibility is that it's implemented in terms of, and we'll talk about them, linked lists, where it's, you know, we're giving up some speed for flexibility, for malleability. Okay, so instead of requiring contiguous memory, linked lists just say we're going to make each bucket know about the next bucket. Okay, they'll know how to get there. All right, so it's kind of like when you go on one of those scavenger hunts where you got to go to one place and that place has a clue that tells you the next place you go to, which has a clue that tells you the next place you got to go to. That's how linked lists are kind of built. Now, that's not the most efficient way to get to the endpoint, right? But it does allow you to store a lot of data in a bunch of individual spaces. So we're going to say that these guys are not limited by original construction. Because if we want to just add a new clue to the end, we can just point it to another place, right? No problem. I only need to find 32 bits to hold another integer. I only need to find, well, it's probably more like 48 bits or something like that, because not only do I need to store the integer there, I also need to store the clue to the, to the next bucket. So I need to know about some additional stuff there. So it's a little bit higher memory requirement on a per bucket basis, but I've taken away that requirement of contiguous memory. So not limited by original construction, and relatively speaking, slow. Now this relates back to this previous slide though. This slide, speed. What does slow mean? Would a human, if we stored 100 integers versus inside of an array versus 100 integers inside of a linked list, and we searched through that linked list using what we're going to presume is our most inefficient searching algorithm. Okay, slowest possible way of searching through stuff. Do you think a human being is going to notice how long it's going to take a computer program to search through 100 elements in an array inefficiently versus searching through 100 elements in an array list or a linked list inefficiently? Are we going to notice? No, computers are fast. Every 5 minutes when the new machine comes out, they're talking about, oh, this version of the Intel Core i7 processor is, 13 times faster for this very specific type of computation that you're never going to do. But if we measure that, we can talk about these huge, awesome numbers. Okay, but every new thing that comes out is faster. It's faster. It's better battery life, or well, this one has worse battery life apparently, but I've actually never used it not plugged in, but except that this is my first time. I'm at 66%. We're an hour in. Oh, that's not horrible. What is this? Does it tell me how long until empty? No. It's a surprise. It'll just be a surprise. Whoa. All right. So, yeah. Plus, this gigantic trackpad ticks me off. You can't do anything in here without trackpadding. I mean, the trackpad is this is the only part of the laptop that's not covered by trackpad. That's stupid, isn't it?
Yeah.
Who needs a trackpad that big? I mean, you got an older Mac. I mean, have you ever sat there? I mean, actually, her Mac is quite a bit older. She has the SD slot on the side of it. Yeah. So I mean, have you ever sat there and said, this trackpad just isn't big enough? No, it's yeah, but I mean, who's going to use that? You got buttons on yours. I don't want buttons. I mean, I used the Dell one time. I got a rash.
I can touch my touchpad. I don't have to use.
Yeah, but you don't want to. I mean, or you gotta use that hand sanitizer stuff or whatever, right? Like immediately, right?
I think it's because they want people to be sold on the hand gestures. That's the only reason I can see why it would be so.
Well, it took away one of my hand gestures. I used to use that down swipe thing all the time. which would only, if I did the down swipe, it would only show me the, I don't remember what it was called. They had some stupid name for it, but it would only show me the screens of the current application. So it would show me all of the keynote screens. So I would only have to be looking at these 4 instead of every screen I have open on my application. Look, this installer's not even done yet.
It's probably something you can change in like mission control.
Well, I'm sure that's true, but why should I have to? This is dumb. I probably have 3 different control panels now for this giant trackpad. Like trackpad quadrant 1 control panel. All right. So this kind of gets back to this idea that human beings are only going to perceive speed differences sometimes, right? So if we're storing a relatively small number of things, we can throw speed out the window. It doesn't matter. Computers are really, 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 really fast. That's why we use these things as tools, okay? Because they can do mundane mathematically tasks really, really, really fast and without making mistakes like we would if we had to do that kind of stuff. That's what computers are good at, all right? So why should we try to be nice to, really computers are like our slaves, right? We don't need to be nice to the computer and say, well, let's give you a break. I'm gonna use arrays this time. That way you don't have to jump around in memory. We don't care, okay? We want to abuse this computer. We want to get our money's worth out of that new Core i7 blah, blah, blah gigahertz processor, okay? Because that's your job. Your whole job in life is to sit there and do number crunching for me, right? We're very mean to our computers. You probably aren't. You probably clean it every night and
Rebuild it.
there's massages. There are massages involved. That's creepy, but I get it. It's a thing.
I rebuilt all of my computers over winter.
Even your laptop?
Well, I mean, reload operating system.
Oh,
Yeah.
well, when I run Windows, even on the Mac, if I'm doing development on, because the main reason I use a Mac is I tell people it's 2 machines for I used to say price of 1.7. Now it's 2 machines for the price of 2.2. Because of the new price tag for these new things. Because I do a lot of work for iOS development as well as I do .NET stuff, so I need to have both sides. So it's I don't have to carry around 2 machines. But the punchline is if I'm doing a lot of .NET development on the Windows side, I'll reload the OS after a month or something like that, even with antivirus or something. It's just, and that ultimately gets back to the old argument where the Mac people say, well, there aren't viruses. Windows is just such a big, much larger target. It's not that Windows is a crappy operating system. It's fine. But if you're, one of these jerks who writes viruses, you're going to write it for the, 95% of the people that are running Windows, not for the 4% of the people running the Mac. And that 4%, that's the new grown number. It used to be like 2% or 1%. I'm just waiting for the day when you go into the Apple Store and they actually have Kool-Aid there. Because somebody's drinking that Kool-Aid, right? Going into a Mac store is an experience. It's similar, or an Apple store, it's similar going into a Radio Shack. How many of you have ever been in a Radio Shack? There's a vibe, right? Radio Shacks have a vibe. So it's like well, no, it's almost like a geek culture. There's like a geek culture to it, but I'm talking about for fun, I solder things onto breadboards. Geek culture, like that. It's not necessarily a bad vibe, but it's a vibe. It's a thing. It's measurable. And the Apple Store is the same way. You don't even know what that vibe is. It was like a hipster thing. Like the people who work in an Apple Store would be the same people you would expect to find as baristas at coffee shops that also sell pot. Right.
Same level of education too.
Well, maybe. Really in any store. You can sit there and you can make fun of Best Buy employees and stuff like that. But pretty much any of those stores, you're going to have 1 or 2 all-stars, right? 1 or 2 people that really know their stuff, and they're doing that because they're in school or whatever. But then the rest of them are, it's the Best Buy training program they went through. So it's the luck of the draw. Sometimes they go into Best Buy and they just screw with them. I'll go up to like a machine. I'll ask questions. I'll just ask these like stupid, ridiculous questions that like don't have answers. How many gigahertz does this keyboard have? And then someone will give me answers. Oh, well, that one's the new model. It's like it's a 2.4 right there, and you're good with that one. All right. So when do we care about speed? Sometimes. When do we care about memory? Sometimes. When do we look at data structures? Well, first of all, we're kind of talking about data structures in general. I've kind of shown you, really almost that decision-making thing. When we look at arrays versus array list or linked list things, two things come to mind. For arrays, I've said these guys are fast, but let me go ahead and throw another statement in here. We're going to say these guys are memory inefficient. Array lists are slow, but these are memory efficient. So that kind of goes hand in hand with those two slides of do we care about speed, do we care about memory? And the fact that the answer to both of those is sometimes. That means sometimes things like linked lists are the right tool for the job. Sometimes they're not. Okay? Just like a power drill, for a screw gun, that's not always the right tool for the job. Is it? You think always. I'll give you an example. Okay. So you get one of those power drills and you have it on the high speed, right? Actually, it's even worse when you have the high torque. But the high speed, that's the less controllable, right? You got a high speed, and you're screwing on one of those the little plastic light switch. Oh, you're gonna go right through that thing, into the wall, and then there's electricity stuff back there. So when you hit that, you blow back across. Yeah, my wife can tell you the story sometime. I was just taking out the wall. That was the last time I did anything near electricity. Yeah, now I either hire a professional or I get a student to do it because I don't care about their lives. Yeah, all the wiring of my boat was done by Nick Largent. Also a true story. I do care about his life, but I find when he gets injured, as long as he doesn't, really get injured, I find it hilarious. One time he was touching a spark plug when I guess I wasn't supposed to turn the key yet. He didn't say when. He was hopping around pretty good. Oh, those are the days. All right, so these are real decisions we have to make, and one thing we want to consider is that arrays are not bad. They're just sometimes not the right tool for the job. Make sense? All right, so one of the things we're going to be looking at in here, and we're going to be making some of the assumptions that, because we want to work with linked lists, we want to work with stacks, we want to work with queues, with trees, we want to work with these different things, so we're going to pretend like they're the right tool for the job. Because we need to learn about them, right? Okay, so we're going to assume that the thing we're doing is this drastically huge thing or whatever. Okay, so for your homework, make sure you get the book, and I want you to read just the Java section. So see like 1.1, 1.2, 1.3. These are all the same content. So I want you to read the Java section for 1.3, 1.6, and 1.7 for next class. Okay, so you're gonna get an introduction to searching algorithms. You're gonna get a refresh of the binary search, even though we did it like 2 semesters ago. Okay? And then you want to get that intro to big O notation, which is kind of our measuring stick for the complexity of an algorithm. Okay, and I'll say there might be a quiz. So it's a threat. It's a true threat. All right, I will see everybody on Thursday.